Hello everybody, in this video I want to look at the factorial. So in part 1 of my combinatorics series I defined the factorial as the product of the n positive integers that are less than or equal to n. So n times n minus 1 times n minus 2 dot 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 times 2 times 1. We also defined it as the number of ways to arrange indistinct objects. Now we also defined it recursively. We have n minus 1 factorial is equal to n factorial divided by n. Using this definition, we can compute 0 factorial, which is equal to 1 factorial over 1, which is equal to 1. Now, the reason why we have to do this is that this definition assumes that n is a positive integer, so we can't just plug in 0. But intuitively, if we're looking at the number of ways to arrange 0 objects, it's just 1, because you just can't do anything. But I mean, that's just, there's only one possibility. It's hard to explain. So now we've extended the factorial to at least non-negative integers, but what about negative integers? What about fractions? What about anything we want? The factorial is such a discrete function, but there's many applications to it, and it seems like there could be a way that we have a function that defines the factorial for more values than just the integers. And in fact there is, and it's called the gamma function. The gamma function is, roughly put, it's equal to n minus 1 factorial for every positive integer input. So if we put in 1, we would get 0 factorial. If we put in 2, we would get 1 factorial, and so on. But also, it extends to, we can put in any value. And the definition of the gamma function is by an integral. It's the integral from 0 to infinity of x to the n minus 1 times e to the negative x dx. And it's pretty straightforward to show that this always evaluates to n minus 1 factorial for the integer values. Like if we just, like for n equals 1, then this is just x to the 0, and so that just goes to 1. So we're just integrating e to the negative x. That's definitely doable. And for any positive integer power, we can just look at, integration by parts, especially the DI method. The DI method just kills this integral, and we see that it does, in fact, evaluate in the end to n minus 1 factorial. Now, another way that is defined is that it is the only function such that satisfies gamma of 1 equals 1 and gamma of z plus 1, my bad, gamma of z plus 1 is equal to z times gamma of z. It is a unique function that satisfies both of these criteria. And so let's say, for example, we wanted to calculate, well, first let's see if we can calculate this gamma of 1/2. So using this definition, we would say that's equal to negative 1/2 factorial. Well, let's see, this is equal to 0 to infinity x to the negative 1/2 times e to the negative x dx. So we want to compute this in some way. Well, this x to the negative 1/2, usually we only see 1 over square root of x when we take the derivative of square root of x. So maybe the substitution u equals square root of x will take us in the right direction. We see that our boundaries stay the same, because from x equals 0 to infinity, we have u equals 0 to infinity. So then we get that du is equal to dx over 2 root x. So that will get rid of this factor entirely. In fact, we'll just be left with a constant factor of 2 on the outside. Then we have e to the negative x, which is e to the negative u squared du. But this is the Gaussian integral. However, well, it looks like the Gaussian integral. However, notice here we're going from 0 to infinity. In my video on the Gaussian integral the other day, we went from negative infinity to infinity. However, we can notice that the Gaussian integrand, I guess I should say, is an even function. So multiplying this by 2 is the same as saying this is from negative infinity to infinity. That is a property of integrating even functions. So we get e to the negative u squared du, and I proved in my other video that this is equal to the square root of pi. Wow! So negative 1/2 factorial is equal to square root of pi. Now we can look at other half integer evaluations of the gamma function. In particular, gamma of 3/2, which evaluates to 1/2 factorial, is equal to 1/2 times gamma of 1/2. So that's just the square root of pi over 2. And if we go to a calculator and we type in 0.5 factorial, we get this weird number. And if we multiply by 2 and then square it, we actually get 3.1415. This is pi. So this isn't just some mumbo jumbo that we've made up. I mean, obviously this was programmed into the calculator so that it would evaluate that way, but this is the actual extended definition of the factorial that mathematicians use. In the next video, I'm going to cover maybe some more properties of the gamma function, and in future videos I will be using it to integrate, to solve seemingly unsolvable integral problems, and I will also cover the Euler-Mascheroni constant and use that to solve a particularly interesting looking limit. So I will see you in my future videos. Thank you.